I use this or no? Okay. Thank you. First of all, thank you very much for the invitation to this conference. I appreciate a lot the enthusiasm for this conference, and so start with the presentation today. Today I will show you some cutting edge technologies that in Europe are carrying out about engine fueled with gas, methane, and hydrogen. Starting from motivation why we are working on hydrogen and methane engine. The agenda report a brief description of the context and motivation, in which many information has already said in these days in the previous speech about the required of energy carriers. And then we move to describe some combustion technology to improve efficiency in gas engine and in methane engine and hydrogen. Okay, this slide is already well known from all the audience, because we need to move in the energy transition to reduce the greenhouse gas emission. And we need to switch from an economy based on use of fossil fuel to a renewable and circular economy in which the energy is totally renewable. In this process, we can see that also this slide is relative to Europe situation, but is similar for other countries, that the transport sector account about 20% of greenhouse emission with respect to the total. And so this is a not negligible sector in terms of contribution, and that require attention in improved technology for the energy transition. Sorry. Looking to the transport sector, here there is a breakdown of the contribution of different sectors, and you can see that the road transportation represents the most important part of the total greenhouse gas emission, and in which 6% are for the car, and about 50% for heavy-duty truck, and 11% for light-duty vehicle. But while for cars we are looking to a moderate transition, at least in Europe, toward electrification, battery vehicle, and so on, in the case of heavy-duty truck and light-duty truck, most of the market is still remain on diesel and part on natural gas. Both are fossil source. But Dr. Chiara Guido already showed this information in the first day of the conference. So we need to work to improve this sector of on transport, because it is a so-called the hard to abate sector. And this is why, because most of the vehicles are fueled by diesel. What are the solutions? Here we report the conventional technologies that exist in the heavy-duty transport sector, the diesel engine, of course, diesel fuel, and and part of the market is related to the CNG and LNG gas. For both these solution, of course, they are applied overall. They already, due to the long history of technology, they have a low total cost ownership for customer, because the engine cost is cheaper with respect to other solution, and also the fuel is cheaper. Has a fast refilling time, and of course we know that has a very large network for infrastructure of refuel. The other solution reported on the right, we have battery electric vehicle, hydrogen internal combustion engine, and hydrogen fuel cell. Each one has pros and cons and uncertainty for the future market. For example, for battery electric vehicle, that is generally interested for urban and regional transport. They have a high product cost and a medium total cost of ownership. Slow refilling time, we know the time that is necessary to recharge the battery, limited refill network at the moment, and limited customer acceptance. That in this sector is the main important driver. In the heavy duty sector, the driver for selling vehicle is the total cost of ownership, is the first one. In the hydrogen, for hydrogen internal combustion engine, the situation is a little bit different, because they has a medium of production cost with respect to battery and fuel cell, and a medium total cost of ownership. Has a fast refilling because it is a gas fuel, but the network is not available at all. And the customer acceptance is not known at the moment. The customer is waiting for the infrastructure and also for the cost of hydrogen. For fuel cell, the similar situation. The main difference with the internal combustion engine is high production cost and medium total cost of ownership. But why, after a very brief observation of alternative technology for heavy-duty engine, we ask why we need renewable fuel. A simple explanation is reported here. Here there is a plot of the renewable energy produced in Germany on 24 hours daily, weekly, and seasonal. And you can see that there is a very variation of the renewable energy producer. So this means that to satisfy the energy demand, at least for the next decades, is necessary to have energy for renewable energy system, to have or electrochemical storage or chemical storage. Okay, and then in this in this scenario, the production of green hydrogen and at the same time biomethane, so renewable methane, could be two alternative solutions, or a part of the solution to increase the consumption of the renewable energy. But what are the situation about the use of hydrogen and by renewable methane? About hydrogen, we have said before what are the main for hydrogen internal combustion engine. We already said what are some benefits with respect to the fuel cell or battery electric vehicle. It's possible to have fast refilling, competitive product cost, and at the moment in Europe they are considered zero emission vehicle, because the CO2 produced by hydrogen internal combustion engine is only from lube oil that account about 3 gram per 3 gram per kilometer of vehicle. Below this limit, the vehicles can be considered as zero emission CO2. For methane, again, it can be a solution because when you refill a methane vehicle with biomethane, the vehicle remains at competitive product cost because we have already a supply chain. There is no compromise in terms of driving range because with LNG you can have a mileage similar to diesel. And the most important thing is that it can be used as existing infrastructure. It can be mixed with the fossil fuel, for the fossil methane, for natural gas, without any modification. So it's very fast to introduce in the network. And we have the capillary infrastructure for distribution. This is why the interest in increase in development internal combustion engine and methane engine is still strong, especially from industrial sector in Europe. But what do we need to do about engine on this scenario? The most important aspect now is to increase the efficiency of the engine. So to reduce the fuel consumption when the engine runs, to reduce the pollutant emission for social acceptance of the engine, possibly to near zero level. What means near zero? Okay, it can be discussed, but what I can say you is that with the Euro 7 level, Euro 7 regulation in Europe, the level of emission in terms of NOx and PM can be demonstrated that are below the ambient pollutant produced by other sources. This is demonstrated in some cities which for ultra low emission engine the contribution of the single vehicle to the ambient condition is quite negligible. But of course, there is a need very advanced technology for control the pollutant emission. Why important to increase the efficiency? Here you can see a breakdown of the total of the factor that contributed to total cost ownership of the vehicle, and with respect to the car, in which the cost of the fuel is marginal with respect to on the total cost ownership. For commercial vehicle, the fraction of the cost of the fuel is quite high. So any improvement in efficiency of the engine reduce the cost of the fuel over the life cycle of the vehicle, and then bring the vehicle to be more competitive. And this is a graph that provided the response to discuss before what is the how the hydrogen so which is the why hydrogen is in a certain way, because at the moment the hydrogen of the cost is very high, so it's necessary to reduce the fuel cost to be competitive with diesel. And the difference between hydrogen engine and fuel cell and the successful in the market between these two technologies, it will be will then depend on the fuel cost, because fuel cell has a high efficiency with respect to internal combustion engine, but internal combustion engine has a low cost. Depending on which will be the fuel cost, the total cost of ownership of the two vehicles change between them. And so in some cases it could be convenient to buy fuel cell, in other case it could be convenient to buy hydrogen in internal combustion engine. Here is a slide in which there are items in the topic on what, where we are working in terms of development of technology, starting from improvement of fuel injection process using combustion vessel to study the optimization of mixture of fuel of injection fuel with air. Oops. Okay. This is relative to hydrogen. We are working also on improvement on engine cycle operation control, because when we work with hydrogen, especially in ultra-lean condition, the cycle-to-cycle operation becomes an issue. Another important point is the optimization of lubrication oil, because for dedicated hydrogen, because it requires a change in formulation to reduce to limit the interaction between hydrogen and fuel lube oil molecule. Another important part is the compatibility of material of engine component with hydrogen, because you know that is one of the most issues using hydrogen in the engine is the sorry, I don't remember, the infragilimento. So the material can reduce their properties in terms of robustness, and it's necessary to use a special material for use hydrogen in the engine. Improvement of a filter treatment system dedicated for hydrogen, and another cutting-edge combustion solution is direct injection deficit combustion of hydrogen. I'll show you some results about this point. On the side of a methane engine, some point in which we are working to improve this technology, advanced after treatment to reduce the particle and gases pollutant, and in the yellow box, 3 points in which we are working to improve the efficiency of the engine. One is the use of pre-chamber system, another the corona ignition system that I show you some picture, and advanced piston ball design to improve turbulence. Here a picture of our engine. First of all, we thanks a large project in Italy that is named the Sustainable Mobility Center, that is a partnership of university funded by Ministry of University with very high funding, in which we have the possibility to realize very advanced instrumentation in the labs. Also thanks to Pierpaolo Napolitano, Davide Di Domenico, and Daniele Cervone, that are the guy that has really worked on this result. Few words about this facility. You can see here, this is an heavy-duty engine with 2 liters of displacement, and the particular is that we designed, developed, and manufactured all the engine, of course, with the support of some customers, but all the part of the test labs is a proprietary of SEMS of our group. The reason is why is because we want to have a platform with the total control of the hardware and software in order to test disrupt technology or new components that has to be difficult to test when you have a complete multi-cylinder engine already prepared by manufacturer. A brief view of the layout of the engine in test lab. This is the oil circuit that is totally controlled in terms of flow and condition of the oil in all parts of the engine. The same is for coolant, and this is the layout of intake exhaust and EGR system, totally developed in-house. About the software control, it is developed based on the national Compatrio system. This is a picture of the software that we developed on the national, based on LabVIEW, to control both the auxiliary system and engine, but also the injection system. And for diagnostic of the thermodynamic parameter inside the cylinder, we use AVL side. Okay, some results, very spotlight on the different technology that we are working on. The reason why we are working on this is on the use of engine with dilute mixture. So to lean the combustion, because leaning the combustion, so use lean air fuel mixture, increase the efficiency. Why? You can, you know that to increase the efficiency of the engine, we have many parameters: air fuel ratio, leaning it, increase the compression ratio, reducing the pumping loss, and reducing the heat losses. But which is the main driver to increase the efficiency? The main driver is reported. The main driver you can see here. This is the formula of theoretical efficiency of the thermodynamic cycle of the engine. And you can see that in the formula there is the gamma, the ratio between two thermal coefficients. In this graph, you can see that when the engine works in the stoichiometric condition, the gamma is lower. When the stoichiometric product, gamma of the stoichiometric product, and the gamma of the air. When you work with the lean or lean air fuel ratio, you are in this range. And leaning the mixture, you increase the gamma, and so you increase the efficiency. This is why the possibility to move the operation of the engine in lean condition is the main driver to increase the efficiency. By the way, these are some results from single cylinder engine, and you can see that when you move from stoichiometric condition to lean, there is a progressive increase of efficiency. This is the dilution is obtained leaning increasing the air in the mixture, and here is reported the increase of the cylinder pressure due to the increase of the boost to have the more linear combustion. The same occurs when instead of air you use AGR. Okay, when applied exhaust gas recirculation, you can see that there is an increase of boost, and the duration of the combustion increases. This is the time, the crank angle delay between start of spark advance, start of combustion. But in any case, also with EGR, you can see that there is a progressive increase of the efficiency, less than leaning the mixture with the air, but in a way there is an increase of the efficiency. And that's why we are working on the use of these two leverage to improve the efficiency of the engine. About the fuel consumption, okay, you can see here a progressive reduction of the benefit when you change the load. So for this type of engine, the two leverage provide an increase of efficiency, but this improvement is progressively reduced when you move from low load to high load condition. And you can see here that the leaning the mixture with air is more effective of EGR, because up to 1.3 of leaning of air fuel ratio, of air fuel ratio, the EGR becomes unstable in terms of cycle-to-cycle variation. You can see you arrive up to about 5% of the COV, and you need to stop to increase EGR, otherwise the engine is not more controllable. Then, how to improve the combustion in the lean condition? When you lean mixture, the two main problems are the ignition of mixture. You need more energy to ignite the mixture, and to control the COV variation, so to be the engine more stable cycle to cycle. This means in spark ignition engine to increase possibly two factors. One is the energy of the spark, so more energy is introduced in the mixture as a spark, faster will be the combustion, and so you can increase can more dilute the mixture with air or EGR. Second one is the improve the flame front velocity, so the duration of the combustion. And this is possible with increasing the turbulence inside the cylinder. By the way, the high-speed engine have, especially for racing application, has a very high turbulence to increase the velocity of flame front and to burn the fuel as much as fast possible. The increase of energy produced in the cylinder, it can be done with at the moment we are working on two solutions. One is the corona igniter, another one is the pre-chamber system, while the turbulence is improved by the redesign of the piston sides. About the corona spark ignition system, if someone don't know how the system works, you can see here the two effects of the conventional spark plug and the corona ignition. The corona ignition practically generates a plasma of electrons inside the mixture. Some plasma spark are named streamer, and it is a non-equilibrium and low-temperature plasma, in the sense that electrons are energized inside the mixture, but the temperature of the volume doesn't change more. This is different from the conventional spark. And another important aspect that the volume of mixture in which the electrons are energized is much more large than the conventional spark. You can see here a movie taken with our phone close to our engine. What are the effects of a corona ignition? The effects are that are reported here. Practically, when you switch from spark plug to corona, there is an increase of an increase of the spark velocity or the combustion velocity, because this is the sparking time of the conventional plug, and this is the spark timing of the corona ignition. And you can see that is at the same cylinder pressure, it can be retarded. So reducing also the classical problem of combustion spark ignition engine terms of knocking and in terms of knocking. However, when you move in lean condition, at the moment there is not the same performance of the spark plug because the cylinder pressure is a little bit lower here. But this is why it is also retarded. So these are the two tests are produced, are collected at the same phasing of the center of combustion. And anyway, when you see on the results in terms of ESFC, so specific fuel consumption, and the COB, there is a slight benefit at the moment for this type of engine, methane heavy duty, when you move from spark plug to corona ignited. This is a little bit different with experience on gasoline high speed, because generally when you apply the corona and high speed engine, there is an improvement of performance. In that case, that is a low speed heavy duty gas engine. We don't see at the moment a very strong improvement, but we are working on this to evaluate which is the limit to exploit better this type of technology. That again, in high-speed engine, demonstrate a great potential to improve the combustion velocity. Another technology already named, called by Hans, by Professor Behmen before, is the pre-chamber system. What is the pre-chamber system? Pre-chamber system practically, instead to have the spark plug inside the cylinder, you have a cap, so a small volume in which the spark plug is put in, and there are two versions. One, there is only the spark plug. In this case, the pre-chamber is named the passive pre-chamber, in which the fuel air mixture arrives from a combustion chamber inside the volume. And second one, you have another version named active pre-chamber, in which there are both fuel injector and spark plug. And you can control the fuel mixing inside the pre-chamber that can be different from the fuel mixer inside the main chamber of the piston. You can see here a sketch of an active pre-chamber. This is a sketch of a large bore marine. What are the potential of the pre-chamber system in lean condition, and why lean condition are important? These are some results, a picture that show the capability of operation with the lean using active pre-chamber for marine engine. When you move to ultra lean condition with air fuel ratio about 2.2, from stoichiometric condition, the NOx production goes down until quite zero, and the efficiency increase for the reason explained before. But we have a strictly operative window in which these two results can be obtained, because for ultra lean condition, but it depends on the fuel, this is for methane, ultra lean condition, the misfiring occurs. Otherwise, for more rich condition, you have a problem of knocking for when you arrive too high in terms of load. The potential of pre-chamber, it can be shown in this slide. This is the report of Mercedes AMG Formula One engine in 2016. That was one of the first sport car engine in which the active pre-chamber was applied, demonstrating the capability to arrive to 50% of efficiency for an engine that run at about 13,000 RPM. And this is why the main reason, one of the two main factors, apart the use of turbocharger, friction reduction, and so on, was the lean combustion and the pre-chamber application, in which you can see the step of increase of efficiency. And now this technology is developing to extend their application from sport car to the normal production series engine. So, apart of this spotlight, what are the results in our heavy-duty methane engine? Is reported here. Pre-chamber increased the combustion in first phase, increase the speed of combustion, the release of it in the first phase of combustion. You can see here that with the stoichiometric condition, the spark timing can be retarded with respect to the normal spark plug using the passive pre-chamber. And when again, when you go in a lean condition, there is a reduction of the speed, of combustion speed with pre-chamber. About the duration, in fact, you can see that with the conventional spark plug, leaning the mixture, the duration of the combustion progressively increase. But when you switch to passive pre-chamber, from the stoichiometric condition to ultra-lean condition, the duration of combustion increase more than conventional spark plug. Notwithstanding that in stoichiometric we have benefit, because this is 18 crank angle, and here we have about 15 crank angle, so demonstrating the shortening of the combustion. What this occurs because with the pre-chamber, the transmission of the combustion from chamber to the main chamber through the pre-chamber hole is a very complex process, and the scavenging, so the formation of mixture inside the passive is strongly dependent on boundary condition. We are now working on this to improve the design of passive pre-chamber to transfer the benefit observed at stoichiometric condition also in a lean condition. Finally, for methane, some spot about what is necessary to improve the piston design, because piston design generally control the turbulence inside the engine. This is mainly valid for low-speed engine like. And these are some sketch of the different piston shape that we are studying. As a result of the potential of this leverage to improve the efficiency, these are the traction trace of two different piston design at the same engine condition. And you can see that one is increased turbulence. When turbulence increase, also the combustion speed increase and the pressure cylinder increase. And you can see here the difference in heat release rate, reducing the fuel consumption. Generally, we also measure the possible reduction of up to 2%, just changing the combustion, the piston body. Okay, these are some spot for we are 5 minutes for closing. Some spot about hydrogen experience. These experiences are carried out together in cooperation with FKPS, is the Department of Engineering Automotive in Stuttgart. Thanks to Professor Ander Putzer for hosting our PhD Davide Domenico that has carried out the work in in laboratory of KBFS, and Bayer for the cooperation with Davide. This is the sketch of the engine used for experience hydrogen. This is I think the Porsche, a single cylinder derived by a Porsche engine so it says high-speed engine with dedicated for sport car, and the architecture has a direct injection of hydrogen at high pressure up to 115 bar, and this is the scheme of a combustion architecture. These results are published also in energy environment combustion journal. And okay, what we did, we tried to control the combustion of hydrogen not with the total premixed fuel, but injecting the hydrogen around the top dead center at high pressure, like diesel, and sparking the mixture across the injection duration. So imagine, you can see here the sketch. This is top dead center. The injection duration was facing around top dead center, and the spark was activated between this time frame. Okay, for different steps. The different step you can see here, 20, 46, and so on, 120. With respect, this is a delay of time with respect to start of injection. So for 100 and 120, you spark the mixture at the end of the combustion, end of injection. This means that you have a premixed mixture inside the cylinder, but not homogeneous, totally stratified, because the hydrogen is progressively distributed in the cylinder. For 20%, you spark the mixture just some milliseconds after the start of injection. So the rest of the fuel is injected when the combustion starts, generating a diffusive combustion of the hydrogen. You can see here a sketch of different distribution of the fuel with respect to spark. And we named it jet. The difference was named jet, 20%, 40%, and so on. What happens when this occurs? It's very interesting, the results, because when you spark at the end of injection, you have a classical premixed combustion. So the whole mixture burns very fast, even if it's all very stratified in the engine, so it's not homogeneous, but burn very fast. When you move from the end to the beginning of the injection, the shape becomes like a diesel combustion, with the premixed phase and diffusive slate. This means that the part of the hydrogen that has injected before the spark burn immediately, independent on timing, and the rest burn like a diesel. And this is a very, very interesting results, because the duration starts from increase as to when the spark is retarded with respect to start of injection. The indicated efficiency increase with the load, but decrease when you move from a total a premixed combustion to a diffusive combustion. But anyway, you reduce the problem of the hydrogen engine, because you don't have auto ignition, and you don't have reduced NOx formation, as you can see later. In fact, Yes. Another very interesting result is, as I said before, is that for all setting of Spark, the duration of premixed is always the same. So this means that whatever is the quantity of hydrogen that you injected before the spark, and it's burned immediately because hydrogen is very, very fast. Okay, just to final, it's another very interesting result is that when you move from high premixed combustion to diffusive combustion, the NOx tend to reduce. One main comment on these results, because the capability to implement this technology permit to transform a conventional stoichiometric spark ignition hydrogen engine in a diesel engine, in which the efficiency of the engine becomes controlled by the quantity of the hydrogen that you put inside the cylinder, so depend on the velocity on which the hydrogen is delivered inside the cylinder. And if the technology of high injection hydrogen engine will improve, it's possible to reach the efficiency of diesel engine using only hydrogen. And this it will be very, very great results. Okay, just to, sorry if I would later. I would close only a main keynotes for this. The complexity of energy transition require many motivated and skilled young scientists because it's a very, very complex problem. So for the young people that are here, I hope that this will be the presentation, and also these spots will stimulate your passion and interest for this complex problem of energy transition. Okay, this is a team of works in our advanced powertrain, and finally, again, thanks to most national sustainable mobility center in Italy for supply our activity in funding and the new research. Thank you very much for your attention.
Agradecemos a Carlo Beatrice por su presencia.